Okay, we're all good with the QR code? We all scanned it, hopefully. Okay, before we continue with the handout, I just wanted to announce that we officially have our tutoring schedule fixed. Remember that every tutoring session is gonna be at the SOC, which hopefully you guys know where it is. Does anyone not know where it is? Do you have any trouble finding it? So the SOC is gonna be the building, the new building right across from the breezeway. You're just gonna keep crossing all the way until the end. You're gonna pass the gym and it's gonna be the first building before you reach the garage. So yeah. So that means that Christian actually is working today from 12 until 2, so right after my my SI session. So you guys are more than welcome to join, but I would highly recommend you to go to lecture first and then join him. So do we have any questions on tutoring at all or SI? We're all good? Okay. What do you mean? In this room? For Fridays, yes. So the new schedule, hopefully you guys saw the announcement. On Fridays, we're gonna be here. And then Mondays and Wednesdays, we're gonna be in General North 101. Okay, so that's the big lecture hall. Okay, so during last SI session, we were talking about counting signals for both HNMR and CNMR, right? Now, do we have any questions on the problems we worked on the previous session? We're good? Okay, so now, the ones that he usually likes to put on the test are the ones that we didn't cover. The cyclic ones that are shown with stereochemistry, which actually probably you've seen at least a triangle looking shape before in Orgo 1. So let's start with the cis version of the molecule. You have to know the number of signals for both cis and trans isomers. Okay, so just by looking at molecule H, how many HNMR signals do you guys think there are? Or do we all agree? Is it 4? Okay. Do you have any planes of symmetry there? How many? 1, which goes right here. And then let's just start counting our signals. I'm gonna delete that. Right here. Because you're not creating equal images on both sides. Remember that symmetry needs to be equal images on both sides, mirror images. So because we don't have this method group on the other side here, there's no symmetry. Okay. So let's just highlight our signals. So the most obvious one is always going to be the method group, the one that's odd looking, let's say. So that's our first signal. Then we have our hydrogen star dash, the ones that are connected to the method group. And then the last two, why are they different from each other? Why aren't they not part of the same signal? Exactly. It's all about the reference that we have to the method group. So in this case, that orange hydrogen, the one that's on a wedge, that one is way closer to the method groups because they're pointing to the same side. As compared to the one in the bottom, which is dash. That one is slightly further away from it, so they are exposed to different environments. Again, this is just happening because stereochemistry is being shown. If everything is planar, then you can't really tell. But most of the times you're gonna find stereochemistry being shown, so please be careful with that. Yes, but your professor is not gonna make it as easy as that. He likes to show stereochemistry in this case. Okay, so we said 4 HNMR signals. What about CNMR signals? How many do we see? So in this case, we have 1, 2, and 3. Because remember that we had a plane of symmetry right here. Whoops. Let me make it smaller. There we go. So that means that the carbons are mirroring each other. That's why I'm not counting the ones at the bottom right. Okay, so far questions on the cis isomer. That's usually the easiest ones to see. No questions, we're good? Okay, now let's look at molecule K. Slightly different. This one, it's the trans isomer. So how many H and M signals do you guys see? 3, 4. I heard another 4. 3 now. Be careful with stereochemistry. Any other answers? To 3 or 4? We think it's 4. Okay, so first of all, are there any planes of symmetry in here? No, they're trans to each other, so they're not going to be equal to each other. So let's do the same thing. Let's start with the method groups. The method groups, they're automatically going to be in a separate environment. Oops, there we go. There we go. Okay. Now, usually whenever we get to trans isomers, I like to draw the molecule in something that I like to call the chair-like view, which is the one at the bottom left side, because it's easier to see wedges and dashes and that way. Okay. Now I can explain it in both sides if the chair view doesn't work. Okay, so just let me know. So in this case, these two guys are the same exact thing. Now, these two guys, are they going to be the same signal, different signals? What do we think? Why the same? Exactly. So overall, even though they're trans, they're exposed to the same exact environment. Because if we look at this guy, the wedge hydrogen in here, that one it's next to one method group and across from another method group. That's its environment. Now, the one at the bottom, the one that was dashed, this guy, it's next to a method group and across from a method group. So the descriptions match each other, therefore they're exposed to the same exact thing. Questions so far on that? We're good? Do we all see it? Okay, awesome. Now, what about the last two hydrogens? Same signal or different signals? Same signal. Again, same process as we saw before. Overall, they're going to be exposed to the same exact environment. So the one on top, the wedge one, it's next to a method group and across from hydrogen. Same thing for the bottom one, next to method group and across from hydrogen. Okay. So again, always be careful with anything that's cyclic and that has stereochemistry in it. Okay. So any questions on the little cyclopropane? We're good on those? Okay, now let's see a slightly different version. Molecule I. That's your cyclobutane, and this one, it's the cis isomer. How many H&MR signals do you see in total? 4. You guys are absolutely correct. Is there any planes of symmetry in here? How many? Only one. Right across from here. Okay, now, same process. The easy one to spot is always going to be your dear method group. So these guys, they are part of the same signal. Next one is our hydrogen in here. Now, the last two, why are they different from each other? Again. The two guys at the bottom. They're cis and trans, exactly. It's a slight difference, but it's gonna count, okay? And then for CNMR, we didn't talk about that one, actually. How many signals do you see? 2? Which one did you say? Oops. It is gonna be 3 CNMR signals. Same process. 1, 2, and 3. We're only looking at one of those planes because it mirrors, yes. For both cis and trans, it's the same exact thing. It's 3. NMR. And then in here we found it was 3 H and MR. And then very last molecule, molecule J. Cyclobutane again, but now it's trans. How many H and MR signals do you see? Four, did everyone get the same? It is gonna be four as well. Okay, now, again, do we have any planes of symmetry in here? No? Okay, no. First one, the easiest one to spot is always gonna be your dear method group. Now, the hydrogens in here, those are your second signal. And then, now, we have 4 hydrogens left overall. Now, for this one, I'm gonna be using the chair view, so it's easier to see. So I'm gonna look at my wedge hydrogen in here. Okay, I'm looking at that one. That one is the one that's next to a methyl group and next to a hydrogen. That's its environment. Now, the hydrogen here at the bottom, does it have the same exact environment? No, it's slightly different. That one, it's next to 1 and 2 hydrogens in here. Okay, so those two are gonna be different even though they're connected to the same exact carbon. Okay. And then the other wedge hydrogen, the one that's in here, is that one gonna be the same as the orange or purple signal? We're looking at this one. It's actually gonna be the same as your purple hydrogen, because this one is next to 1 and 2 hydrogens. The one at the bottom, the one that has the same environment as the orange one, is next to 1 methyl group and 1 hydrogen. Okay. Okay, questions on that? Yes. So let's just see this guy. And then questions on the H&MR signals. We're good? Do we all see it? Okay, what about CNMR signals? How many do you see? In this case, it's gonna be 3. Because again, same process as we saw with the hydrogens. It's all about the environment that they're exposed in. Okay, so questions so far on any of the molecules that we've covered? Yes. So yes, it's gonna be, for example, this carbon, and this carbon. Because they're gonna be mirroring the same environment as we saw with the other ones. For carbon CNMR, carbon NMR, their chemistry is not too relevant. It's all about the connections that you have overall. Okay. Okay. Any other questions before we talked about an antitopic, homotopic, those guys? Okay, we're good? Okay, no. For this class, we're gonna be using those 4 terms again that you hopefully learned back in Orgo 1. Homotopic, heterotopic, an antitopic, and distereotopic. Now, you're not only gonna be asked to show the relationship between 2 hydrogens, but whenever you're given a molecule, you're expected to automatically use those terms when figuring out the number of signals, okay? Now, what's homotopic? What does it mean? Same environment, same signal. That's it. That's the general broad term that we have. Now, enantiotopic was just a more precise term of homotopic. The only difference is that it creates a possible or a potential chiral center in there. We know that because we do the Q test. Now, what's heterotopic? What does it mean? Should be simple. Different environments, different signals. So diastereotopic is just going to be a more precise term of heterotopic. Now, for diastereotopic, we're going to see two different scenarios. So we're going to wait for the molecule first, because let's start practicing those terms now. Okay, so if we're looking at that molecule, they're asking for the relationship between HA and HB off the bat. What do you think it's going to be? Homotopic? It is going to be homotopic. Now, why is it not an antitopic? What do we notice in there? What was the requirement to be an antitopic? Mirror images, because we need to create an enantiomers. Now, in this case, when we do the Q test, let's say I'm replacing HB with a chlorine. Do I create a chiral center? Why not? What do I need to create a chiral center? 4 different groups, exactly. So in this case, because there's symmetry in the molecule right here, it's not possible at all. Okay, now this one should be relatively easy. Relationship between HA and HB, what do we think? They're just in completely different signals, so yes. They're just gonna be heterotopic. Okay. Next one. The one with the double bond. Homotopic? Do we have any symmetry in the molecule? No. Okay, what if I replace HB with a chlorine? Is that a chiral center? So it's not gonna be just homotopic. It needs to be enantiotopic. Okay. The last molecule in there, HA and HB, what's their relationship? Isotopic. Why? What do you notice? If you do the Q test, okay, you create a chiral center. Is that the only requirement to be diastereotopic? Because so far it's the same as an antitopic. So what was the difference? It has established chiral center, which is over here. So that's the main difference between these two molecules. Okay. Yes. When it's already given in the molecule, when you have a carbon with 4 different groups already present in the molecule, you don't need to do the Q test. Okay, now we have 4 more molecules, so I'm gonna give you 3 more minutes to solve it on your own. 3 more minutes, and then you have to be precise. Homotopic, heterotopic, enantiotopic, or diastereotopic. There's no kind of symmetry and their bond to different carbons automatically. Yes, they're gonna be different signals. Okay, do we need the remaining minute? Do we have our answers? Okay, awesome. First molecule, relationship. Homotopic? Did you all get homotopic? I see some no's. So what did you guys get? Enantiotopic and distereotopic. Okay, so I have 3 different answers. So let's just start doing the Q test. Whenever you're in doubt, always do the Q test. Okay, so previously we were talking about how to assign cis and trans configurations to a double bond, right? Okay, so on the left side, I have a carbon chain and a hydrogen. So what's gonna be my highest priority? The carbon chain, exactly. Now, on the right side, fluorine versus hydrogen. What's gonna be the highest priority? Fluorine. The 2 number ones are pointed to the same side. So this is cis or C. Okay, now I repeat the same process with the chlorine at the bottom and I bring back HA. This time my number 1 is pointing down. They're pointing to opposite sides. So I'm creating the trans or E isomer. Whenever you create both isomers at the same time, this is actually going to be distereotopic. Okay. That's one of the things that I forgot to add in that table in there. You can have 2 possible scenarios for distereotopic, the one with chiral centers or the one with double bonds. Okay. But do not always assume that automatically, as you see, hydrogens just connected to a double bond. They're not always going to be distereotopic. You have to be careful with what's presented in the molecule. Okay, what about the next molecule? What's the relationship? They're just heterotopic, completely different environments. Third one. They are enantiotopic because if I do the Q test, I create both S and R enantiomers. Okay, and very last one, the one with the double bond. Homotopic. Why not distereotopic? What did you notice? There's symmetry. So there's symmetry. That means that I'm not going to have a higher priority on this side. So I can't tell if they're going to be cis or trans to each other. So these guys are just homotopic, part of the same signal. That's why I told you to not always assume that hydrogens part of a double bond are automatically distereotopic. You have to see what's around. Okay. Questions on how to use those terms? Yes. That's just the configuration for a chiral center. Okay. Other questions? We're good? Okay. Now, this one is gonna be mostly memorizing the table, most of it, okay? So for chapter 9, you're gonna have a few numbers to memorize. One of them is gonna be for chemical shift. The other one is gonna be for J values, which we're gonna talk about later on. Now, I'm gonna highlight the ones that are usually most important because they save some time while you're on the exam. So the aromatic, your aldehydes, carboxylic acids, whoops. Ketones, and for CNMR, you don't really need it that much, but the most characteristic ones are going to be aldehydes, carboxylic acids, and ketones. Okay. Now, before, when we were talking about the different aspects of HNMR, and we were talking about chemical shift specifically, we had 2 terms, deshielded and shielded. Deshielded, what was it? How do we know something is deshielded? It's on the left side of the spectrum, yes, but how do I know? Just by looking at a molecule. If it's close to something that has a lot of electron density. So anything that's connected to an electronegative atom or connected to double bonds or triple bonds, okay? That's why, as you can see, aliphatic, that just means a normal carbon chain. Okay, it doesn't have anything in special. But if we compare with something that has a double bond, automatically you see double bond electron density in there. So it's gonna make it more deshielded, which is why you see a higher ppm range as compared to the aliphatic zone, okay? And now, the one that I want to talk about is to compare these two molecules here at the bottom. I gave you already their approximate chemical shift, but you guys have to understand the concepts behind them. So the left one is just a normal carbon chain. So this is just your aliphatic region. Now, the next one on the right, what kind of functional group is that? That's a ketone. Okay, now, ketones, they have a carbonyl group, like aldehydes, carboxylic acid. So why is the ppm value not higher than 2.5? Why is it not around 10 to 12? Because of the double one? The double one will tell you that it's going to be more de-shielded. But in practice, we are going to see that it's not. It's actually to the right of the spectrum. So why? Why is it shielded if it has a carbonyl group adjacent? Because let's compare our aldehydes versus our carboxylic acids. Okay, so let's go from right to left. Your carboxylic acid, this hydrogen is next to an electronegative atom that it's also adjacent to a carbonyl group. So there are a lot of de-shielding factors nearby. The aldehyde, this guy is close to the carbonyl, a de-shielding factor. Now, same process with the ketone. This hydrogen, it's somewhat nearby of the carbonyl, but the main difference is that there's a carbon in between. That carbon in between is going to cause some shielding, some protection from it. So that's why it's not going to be in the carbonyl area. It's not going to be around 10 to 12. It's going to be more shielded. Okay. So questions on the concepts? Yes. No, usually whenever you have anything around 10 to 12 ppm, that just means that you have some sort of carbonyl groups. Okay. It's not necessary to have an alcohol group. An oxygen, yes, because of the carbonyl. Bless you. Question in the back. Number of hydrogens, it shouldn't affect. It's the environment overall that's going to affect it. Okay. Yes. You are right. I had the range wrong. Okay, quick correction. So usually carbonyls in general, they can range from 9 ppm all the way to 12 or higher. So that's the usual range just for carbonyls in general. But the ones that you see in the table in here, these guys, those are more precise, which you're gonna have to know now in this class. Before in Orgo 1, I think they just gave you a general range for carbonyl groups, so that's why I mentioned that. Hopefully you guys remember that, but if not, you're okay with just memorizing the ones on the table, okay? These ones are just more specific to them. Now, as you can see, those are just ranges. They're not specific numbers. But if you already started looking at the practice problems that he posted, they're under modules. Just look for the practice problems. You're going to have a set of problems for every chapter and along with the answer key. Okay, so I highly recommend you to do them because they can be very similar to the actual exam. Okay, so again, please do them. But in some of the questions, you're going to see that they're asking you for the approximate chemical shift. They're not asking for the range. They want a precise ppm value. So later on, we're going to start to work on how to guess those numbers correctly. But it's similar to what we just practiced here on the ketone. You start by first identifying the area that it falls under based on the connections that it has. In this case, if it's just connected to one simple single bonded carbon, then it's going to be in the aliphatic region, okay? Which means that there's a ranking between 0 to 2.5. Now, after you have your range of numbers, now you have to look at what's around. You're going to cover the hydrogens that you have in here, and you're going to see what's around it. If you see any de-shielding factors nearby, like the carbonyl that we saw in here, the ppm value is going to be higher in the range, okay? That's going to be how you're going to solve those questions. carboxylic acids are usually shown between 10 until 12, but if let's say that we're looking at this guy versus a normal carboxylic acid, the one at the bottom, once we cross out the area that it falls under, it doesn't have any other de-shielding factor. So that means that that one is closer to 10. But if we look at the one on top, we are looking at this area again. That's the area that I have. So I cross it out and I see what's around. I have a benzene group, a lot of electron density in there. So it's going to pull it closer to 12. Okay. Yes. No. The only aid that you're going to have is the periodic table. Everything else has to come from your own brain. So yes, it's going to be a lot to memorize. So I would start early on in the semester. If you're good with flashcards, do it. If you're just good with color coding, do it. So please start early. Do not procrastinate. It's going to be a lot of information right before the exam. Okay. Okay. Now, also, if you're more of the conceptual type of student, you can also just base it off what we were talking about, the environments that they're in. The more electron density that you have nearby, the higher the ppm value. So you could have a pretty educated guess based on that. Okay. That's just in case you freak out and can't remember all of them. That's okay. There's another way. Okay. Any questions on chemical shift so far? Yes. Not really. No. So the exam is gonna be, depending on how far along he gets to the chapter contents right before the exam, your exam might contain just chapter 9 or chapter 9, 11, and 12. Okay, so it always depends on the pace that he goes in lecture. It's not set. Yes. So he only wants to test you on things that he already covered. Okay, so even though maybe it's on the syllabus already listed, if he didn't cover it, it's not gonna be on the exam. Okay. Now, for your exam, the only thing that you need to bring is gonna be a calculator for this specific reason. Okay. So I think he already covered this in lecture. He was talking about the ppm. Whoops, equation in here. Okay, now, before you start freaking out, I know that before in Argo 1, we always told you that there was no math involved. This is gonna be the only hard math problem that you're gonna see, okay? And most likely it's just gonna be one question out of the 35 questions you're gonna see on the exam, okay? Now, in this case, they're asking you to calculate the observed frequency. Okay, that's what we wanna find. Difference of a signal with a chemical shift at 1.25 ppm. That's your first value, so we're just gonna start highlighting that. That's the next information that we have. We know what we have to find, and they're giving us a piece of information right now, 1.25. Now, next piece of information that they give is that they're using a 400 megahertz NMR spectrometer. That's my next piece of information. You're always gonna be given at least two values, either observed frequency, chemical shift, or the strength of your spectrometer, okay? Because the equation for your chemical shift is gonna be the following in here. So please start writing that one down, okay? It's important for you to remember it, but again, if you freak out, that's okay. It's just one question, okay? So if this is gonna take you a long time, I wouldn't prioritize it because there's gonna be harder questions without math. Okay, now, that's the given equation, but they're asking us for the observed frequency. So, of course, with some algebra, we're just gonna move things around, and now we get our actual equation to find the observed frequency. Now, this is gonna be where you plug in your numbers given. So we need a ppm value, which we know it was 1.25. And then we need the frequency of the spectrum. Now, the frequency of the spectrum, as you saw in here, it's highlighted. It needs to be in hertz. You need to keep your units. But we were given 400 megahertz. So we have to convert. So that means that before I plug anything in, I have to do my conversion. Megahertz times 10 to the 6 hertz over 1 megahertz. So you just cross out your units, and then you're just gonna be left with 400 times 10 to the 6 hertz. Okay, now everything is in hertz. Now I can plug it back in. Okay, now, hopefully some of you have your calculators on hands, or you can use your phone as well. So what number are you finding right now? 2.5? That one is actually correct. 5 times to the 6 hertz. That's gonna be your observed frequency. Actually, it's gonna be to the 8, not 6. Because the answer, it's equal as 500 times 10 to the 6 hertz. So, yeah. This one is basically just plugging in, it's back to algebra classes. It should be pretty simple. Okay, but again, I know that a lot of people are not the best with math. Sometimes you freak out during your exam. So again, it's okay. It's not gonna be your priority. Okay, he's not gonna be focusing a lot on the math. He's gonna be focusing more on the conceptual stuff. So any questions on the chemical shift equation? We're pretty good. Now, this is the next thing that you have to remember. Remember, first thing that is gonna be in your list to memorize. Chemical shifts. Now is the ppm equation. Sorry, the chemical shift equation. Okay, now, this one, I'm gonna give you guys 5 minutes to try and figure out the ranking. Because I want you to show me which one is gonna be the one that's most D-shielded for CNMR and HNMR. That's the main question, but along the way, I want you to figure out the ranking from most D-shielded to most shielded signal. Okay, you have the table, you have the ranges, so use that as a reference. Yes. Your ketone is most. Yes, you are correct. You use the table, right? Yeah. Yeah, good job. Yeah, you're absolutely correct. Okay, do we have our answers, guys? Are we all ready or do we need more time? Okay, so we have 6 minutes, guys. So let's just go through this before you guys go to lecture. So let's focus on HNMR first. So what's going to be the most D-shielded signal for HNMR? The carboxylic acid, exactly. What's going to be the approximate chemical shift? What's the range? The range is 10 to 12. Okay. Then after the carboxylic acid, what's going to follow? Beautiful. What's the approximate chemical shift? What's the range? 7 to 9. What's next? It's the double bond. What's after the double bond? Okay, so here different answers. So we're just between the last two. 1 and 2. Whoops. We missed the 1, sorry. So yeah, the 1 was supposed to be here, and that's why between 2 and 3. Sorry about the confusion, guys. Because this guy, number 1, falls in the heteroatom region. Now, molecules 2 and 3, what's going to be the name of the area that they fall under? They fall under the aliphatic region. Because remember that ketone, even though it's a carbonyl, they are going to be under the aliphatic region because of the carbon in between that's shielding, that's protecting. But we know that a ketone is going to be around 2.5 as compared to a normal carbon chain that doesn't have anything, that's going to be closer to 1. That's why it should be 2 and then 3. Because this one's going to be closer to 1, this one's going to be closer to 2.5. Or this guy's double bonds, I forgot the exact range, but it's around 5 to 7. I'm sorry? It's actually around here. Oh, well, yeah. If I'm making any mistakes, just let me know because that happens sometimes. Okay, so we have our ranking for H and MR. Is it gonna be the same exact ranking for C and MR? What did you guys find? What's the most D-shielded signal? What's gonna be the approximate chemical shift? It's gonna be around 190. What's gonna be next? Peroxide acid, which is around 180. And then, because we have 3 minutes, I'm just gonna start filling this out because I want to explain one more concept. Okay, now. The most D-shielded signals were molecules 2 and 5, which we were looking at, a ketone and now carboxylic acid. Now, remember what we talked about before. The more D-shielded you are means that the closer you are to some D-shielding factors such as an electronegative atom or something that's electron dense. Now, they both have a carbonyl area. Okay, they have the same D-shielding factor, but then we see that we have an oxygen right here. We have one extra D-shielding factor. So this is going to be the only exception to the logical concepts that we were talking about. In practice, we're going to see that a ketone is going to be shown slightly more D-shielded as compared to a carboxylic acid. Okay, so don't get confused with the concept. The concepts remain the same. This is just your exception. Okay, the closer you are to D-shielding factors, the higher the ppm value. This is the only thing that we see different in practice. So do we have any last minute questions at all? Yes. I don't know the exact reason, so I would ask you, Professor, that one for sure. Because if you just look at it logically, it should be backwards. Okay, do we have any other questions before we go to lecture? We're all good. We're taking a picture of the answers. So we're gonna continue with the handout on Monday. Remember, it's gonna be in GN 101. No. Well, it's good for extra class, but I would mainly focus on what he posted on the mod. So it was, I mean, it's good because I have access to the book. That's the only thing. Then, yeah, I just okay. What I said when I asked you. Review, yeah. It's very short. Yeah, I know. Don't worry, you're good. It's annoying. I know. Yeah.
Really, I was confused as to why number 4 was higher than that. You know, you said, the double bond is.
The double one is slightly higher
Okay.
than a hetero. They're right next to each other.
So what is considered a heteroatom, the aliphatic?
No. A hetero is basically any atom that's not covalent with hydrogen.
Okay, so what would the aliphatic be considered?
Aliphatic is just any simple carbon. any line. It doesn't have any free. It's the same as.
So, okay. So any atom that isn't,
Carbon or hydrogen.
that's connected to a carbon chain is considered an element. Okay.
That one.
Alright.